Hello, everybody, and welcome back to Pre-Calculus with Mr. Beck as we continue our journey through mathematics, where if you need any pre-calculus help, I've got your back and you've got your back. Today, we're going to continue our exploration into polar numbers and polar coordinates and polar equations, which if we take a quick look at where we've been, at the beginning of our chapter 9, what we did is we took what we knew as a rectangular system, which was our Cartesian system, and we converted it to something we called the polar system. And then we worked with some polar equations. One of the benefits of polar equations is if we can write like a circle in a polar form, we are now turning a non-function, because a circle is not a function of x or a function of y, we're turning a non-function into a function where we're going to make it a function of the angle. And because we can open and close that angle, or at least go forward and backward that angle, to infinity or to negative infinity, we're now turning all of this into this wonderful functional notation. And if we could make things into a function, it just makes things easier in the long run when you're talking about higher mathematics. Another exploration into working with polar actually involves complex numbers. And that's what our discussion is going to revolve around today. What is a complex number? First of all, complex number, we are going to write it as the variable z. Z is going to be written in the form of a plus bi, which a plus bi, a and b are real numbers. So a and b are real numbers. Now, another way that you can typically see it is x plus iy, or yi. Now, you heard me say x plus iy. Does it really matter? No, we know that multiplication is commutative, so it doesn't really matter how we write it. Does it matter if we have it as a plus bi or x plus iy? No, it really doesn't. This just represents x and y are also real numbers, but one of the benefits of writing it in this form, and I guess one of the benefits is that we can graph this. And so we're going to look and explore how we graph these as well. I realize this is more of an Algebra 2 concept, but at the same time, we want to make sure that we have a basis or a foundation before we apply graphing and working with the polar form. So these right now are called the rectangular form. And we have two complex numbers, 2 minus 3i and 6 plus 2i. Our first objective is, how do we add them? So if I want to take z1, this is the first problem, z1 plus z2, what I'm going to do is I like to line these up. Now, first, let me write it out this way, because this is what's happening. A lot of times we'll put parentheses around those complex numbers just to represent that this is one number. This one number has a real component to it, and it has an imaginary component to it. So the real component and the imaginary component together form one actual number. So the way that we add these is simply line them up. We're going to be adding like terms, 6 plus 2i. So we add our real component to our real component. 2 plus 6 is 8. Negative 3 plus 2 is negative 1. So we end up with 8 minus I. On to second one. What happens when we subtract? So second thing, z1 minus z2. What we'll do is, once again, I will take my 2 minus 3i, subtract my 6 plus 2i. Now, shouldn't be too hard because this is really just like adding and subtracting common terms, like terms. So as a whole, the skill is more of how do we make sure that we know what we're doing. Z1 minus Z2. And let me go back to the other one and kind of fill that in, Z1 plus Z2. Really, when it comes to adding and subtracting complex numbers, there's really not a lot of difficulty because our real gets added to our real or subtracted from the real. Our imaginary gets added to the imaginary or subtracted from the imaginary. So on to the more complicated. Let's talk about multiplication. Now I say more complicated, but Z1 times Z2, if we write it out as 2 minus 3i, 6 plus 2i. Now what ends up happening here is we do our traditional FOILing. 2 times 6 is 12. 2 times 2i is 4i. Negative 3i times 6 is negative 18i. And then negative 3i times 2i is negative 6i squared. Now let's simplify. 12 minus 14i minus 6i squared. This is great, except I'm going to go back to every complex number is going to have this form of a plus bi. And we don't have the form a plus bi because what we have is this negative 6i squared, which means we're going to have to remember that I squared is equivalent to negative 1. And we're going to explore the graphical beauty of that probably in our second video. But we need to, let's go ahead and algebraically look at I squared to negative 1. So what I'm going to do is I'm going to replace the I squared with negative 1. And negative 6 times negative 1 is plus 6. So this now becomes plus 6. So this is really 18 minus 14. Hi, there's our complex number multiplied. And one last step, let's do some division. I'm going to change colors one more time. So to do our division, z1 divided by z2. So z1 divided by z2, we'd write it as 2 minus 3i over 6 plus 2i. And when I look at that, I'm like, okay, is there really much that I can do with that? Doesn't seem like there is. But I'm going to go back to every complex number is written in the form of a plus bi. So there's got to be a way that we can convert this to its a plus bi form. And to do that, we are going to work with the conjugate, 6 minus 2i over 6 minus 2i. So when we multiply those through, then we get 2 times 6 is 12. Our outer and our inner is negative 4i and negative 18i, which combines to negative 22i. And now a negative times a negative is positive, so that's plus 6i squared. In my denominator, I get 6 times 6, which is 36. And then outer is negative 12i, inner is positive 12i, which everybody, that is the point of why we're multiplying by the conjugate, because those subtract out, minus 4i squared. And at this point, we're going to say 6i squared is equivalent to 6 times negative 1, or negative 6. And this negative 4 times I squared is negative 4 times negative 1, which is positive 4. So that gives us 12 minus 22i minus 6 over 36 plus 4, or 6 minus 22i over 40. Now, this still is not exactly the x plus iy or the a plus bi form. So we would write this as 6/40 minus 22/40 I. Of course, we probably should simplify that. I'm going to work down here. This would be 3/20 minus 11/20 I. All right, I took a long time going into that first problem, but let's go ahead and see if we could streamline this a little bit better. So for part B, z1 plus z2 is going to equal, let's just go ahead and add our real components. That's negative 1. Let's add our imaginary components. We have negative 4 square root of 5 and 1 square root of 5. So that'd be negative 3i square root of 5. A lot of times we're going to write this I before the radical so that it doesn't look like it's going underneath the radical. And specifically, I don't want to see it written as negative 5i because is that I under the radical or not? And a lot of people go, oh, it's obvious that it's not going to be underneath the radical. But it's not going to be quite so obvious when our day 2 exploration is to figure out what is the square root of I. So that's part 1. Part 2, if we subtract, then z1 minus z2. If we take 6 minus 7, or 6 minus negative 7, excuse me, we will get positive 13. And then negative 4i squared of 5 minus I squared of 5 is negative 5i squared of 5. So I know I'm kind of jumping through those too fast, but hopefully it's not an issue. Where we're going to get into a little bit bigger issue is z1 times z2. Let me go ahead and start writing this out. z1 times z2 is going to be 6 minus 4i squared of 5, negative 7 plus I squared of 5. Again, we're going to FOIL. So negative 42 from our first. Our outer is plus 6i squared of 5. Our inner is plus 28i squared of 5. And then our last is negative 4i squared times 5. I probably could have written it out a different way. That's okay. Let's go ahead and combine these together. That would be 34 I square root of 5. And now let's take a look at, I have -4, I have I squared, and I have 5. So that would be -20I squared, which would be a positive 20. So -42 plus 20 is -22. So our complex number is this. And last but not least, sorry, we jumped there. The fourth one, if I take Z1, make that a V, Z1, not times, but divided by Z2, we are going to get 6 minus 4I squared of 5 divided by -7 plus I squared of 5. Now, just like before, we are going to multiply by the conjugate. So that would be -7 minus I squared of 5 over -7 minus I squared of 5. We're going to zoom in here so I have a little bit more room to work with. So our numerator is -42 minus 6I squared of 5 plus 28I squared of 5. And now, as I focus on the last, let me show this in a little bit of a highlighted form. If I take this times this, the square root of 5 multiplied to be 5. I have a -4I. I have a negative I, which is positive 4 times 5, so positive 20I squared. In my denominator, I will get a positive 49. Remember, the whole point of the conjugate is that the outer and the inner are going to cancel each other out. So we have a positive 7I squared to 5 and a negative 7I squared to 5. And then if I multiply the last, it becomes -5I squared. That -5I squared, of course, we're going to convert into a positive 5. So our denominator ends up being 54. Our numerator, if I take the -42 and the positive 20I squared, which this is -20, that would be -62. And then plus 22I squared of 5. And then let's reduce. We can reduce, both of those are even numbers, or all of these are even numbers. So that would be -31, and half of 54 is 27. So -31/27 plus 11I squared of 5 over 27. Now, is that an ugly looking number? Yeah, kind of is. But at the same time, every number can be written in, or every complex number is written in the form of A plus BI. Now, I might prefer this form of it, but at the same time, we want to be able to write any of these numbers so that it would be in the form of A plus BI. And this just kind of shows it. If you notice, I rewrote that just so that we could have that A plus BI form. So, as I outlined, our complex numbers can be written in any of those forms. X is real, Y is complex. Now, R is the radius. What do I mean by that? Our complex form, we are now going to convert into what we're going to call polar. And so that radius, if you look at the complex number graphically, and let's focus on that graphical aspect of it right now, that radius ends up being our distance. Let me change colors here quickly. That radius ends up being the distance from the pole to the complex number. So I told you our whole goal of working with complex numbers is so that we can explore them on a polar level and see what's going on. So on the polar level, we're going to turn our x, which if just a quick recap into how we graph our complex number, we go along our real axis. So the x coordinate is our real axis. And then our y coordinate ends up being our imaginary axis. So that y coordinate ends up being the imaginary axis. So if I want to take a look at, let's say 2 plus 3i, 2 plus 3i can be graphed if we go 2 along the real, 3 along the complex. So 2 plus 3i is this point right here. There's our 2 plus 3i. Now, how this is going to convert into polar, when it comes to polar, our polar is going to say, well, how far out is that z value? That's what we're going to call our radius. And then our theta is going to be how far off of the polar axis, or the positive, or the real axis in this case, our theta ends up coming off of that axis. So we are going to convert and work with these on that level in just a moment. So let's actually go into graphing some of these. Z1, I am going to do Z1, since I have red, I'm going to make Z1 there. So Z1 is 1 plus I, which is simply that point right there. Z2 is what I have in blue. So -4 minus 4i, that means my real component's -4, which is right about here. I'm going to erase that in just a moment. Then our imaginary component is also -4. So if I go -4, what looks like -4, -4, I get to that point right there. And now, here's where our work comes in. Let's actually multiply those two and see what's happening. So if I multiply those two to get Z3, oh, I forgot. Let's actually label this as Z1 right there. And let's label the other one as Z2. And now to get Z3, let's go ahead and multiply these. I made it so these, when you multiply them, are not going to be quite so bad as the examples that we had earlier. Those examples that mainly taken kind of like from Algebra 2, I know they're a little bit harder to work with, but that was the point. So let's multiply these. -4, and I have -4i, then also -4i, then I have -4i squared. So this becomes a +4, so I actually get the number 0 minus 8i. And the question always is hey, can I write this as -8i? Sure, you can. One of the reasons why I like to write in this form is because any complex number can be written in that form of a plus bi. So 0 minus 8i ends up being down here, Z3. All right. Then let's go ahead and do our next example. So Z1 here is going to be 4 square root of 2 minus 4 square root of 2i. So just so I understand what 4 square root of 2 is, because this is not quite so happy of a number that I want to plug in. 4 square root of 2 is about 5.656. So I'm looking at 5.656. And the only reason I care about that is when I go to graph this, 5.656 is, say, about right there. And then I'll have minus that, which if I line this up, I'm going to erase this part in just a moment. So if I line that up over here, and I line that up over here, it looks like it's going to be right on that polar intersection. That's kind of a preview for what's going to happen here in just a moment. I have to get that point back. So there's a connection here, guys. I'm excited. I hope you guys are too. Z2, let's do in this color. Z2 is just simply 2i, which, again, I like to write that as 0 plus 2i. So 0 plus 2i would be right here, because once again, that is the imaginary axis. Now, if I take Z1 divided by Z2, that's my little daughter there, Z1 divided by Z2, if I take 4 square root of 2 minus 4 square root of 2i, and I divide that, that's going to be Z3. If I divide that by 2i, now officially we should multiply by the conjugate. If we multiply by 2i again, or really by I again, it's not going to matter much. I still like to multiply by the conjugate just so that kind of keeps the same pattern. We end up with -8i squared root of 2, and then it would be plus 8 squared root of 2 I squared over -4i squared, which gives us -8i squared root of 2 over a +4. Let's continue that on. And then it's -8 squared root of 2 over that +4, and then we'll flip it around so we can get it into a plus bi form. Also simplify, -2 squared root of 2 minus 2i squared root of 2. Let me clean that up a little bit. So -2 squared root of 2 minus 2i squared root of 2. So what is 2 squared root of 2? Let's just take that answer that we had there and divide by 2. 2.83-ish. So negative 2.83, I'm going to say is about right here. Negative 2.83, also about right there. And I think I was off a little bit because if we match up, we should be right on that polar mark. As I said, that's kind of a preview for what's going on and what we're doing here. So hopefully this was a good, semi-review for you of what it is that we, or what you guys did in Algebra 2. And this is kind of like setting the stage for what we are doing in our pre-calculus as we're converting, or as we're actually going to be working with the polar system, because I know we haven't done that just yet. Simply what we've done is we've reviewed these skills of addition and subtraction, multiplication, division, and then we've plotted the points in the complex plane. Stay tuned as we now are in our second video. This time we're only going to have 2 videos. Stay tuned as we're going to work with those 2 and do some conversions and then find products and quotients.